Hello everybody, it's all good question 2467 most profitable path in a tree. There is an undirected tree with n nodes labeled from 0 to n minus 1 rooted at node 0. We are given a 2D integer array edges of length n minus 1 where edges I indicates there is an edge between a node A to B. At every node there is a gate. The value of this is given in the uh, array amount. If the value is negative, we have to pay the price to open the gate, or if it is negative, we have to pay the price to open the gate, and if it is positive, we can collect the cash reward. Right? So this is similar to a game. So Alice is at node 0 and Bob is at node Bob. So Bob is a variable, so it can be any node. At every second, Alice and Bob move towards an adjacent node. Alice moves towards any leaf node, while Bob moves towards the node 0. For every node along their path, Alice and Bob either spend money to open the gate or accept the reward. If the gate is already open, it means that there will be no cash reward. And if they reach the same node simultaneously, it means that they collect half the reward or they pay half the price. Okay. So if Alice reaches a node, he stops moving. Similarly, if Bob reaches, even he stops moving. Uh, they are independent and we have to return the maximum income Alice can get after she has moved to the optimal leaf node. Okay. Let's consider this example. Bob is at node 3, whereas Alice is at node 1. Node 0, sorry. 0. Okay. So Bob moves from 3 towards 0 and Alice can move towards any leaf node, right? So initially, the path that Bob will go from will be from node 3. He will go from node 3 to node 1 and from node 1 to node 0. So the path that Bob will take. Okay, let's also put steps on these so that we know how many steps it has taken to reach the 0th node. Okay, so this is at step 0, this is after step 1, and this is after step 2. Okay, now let's see the distance Alice can take. So initially Alice is at node 0, right? And she has to pay -2 to uh, open the gate. So at the current time, the total steps Alice has taken is 0 and she has to pay -2 price, right? Okay, and then when she goes to step 1, right, to the next node, at step 1, because she and Bob both reached at the same node after exactly one step, they have to pay half. She has to pay half the price. So her total cost will become half of the earlier cost plus half of the current node's cost. The current node cost is 4, so half of that is 2. So -2 plus 2 will be 0. This is the current total, and the steps she has taken will be 1. Now she has a choice. She can either go left or right. Now, if she goes left, the cost will be the steps will be 2 and the cost will be 0 plus 2. So this will be the total cost. And if she goes right, the total steps will again be 2, but the cost will be 0 because this is already a path that is traversed by Bob. So the total will still be 0. Okay. And on the left hand side, we have already reached the node, so we stop right here. And if we take a look at the right side, there is one more node, so we can again traverse that also. So after that step, the step will be 3. So after 3 steps, the total will be 0 plus 6, the current gate cost. So after adding 6, the total will be 6. And if we take a look at all the leaf nodes, the maximum value that we have is 2 and 6. So the total we can obtain after traveling will be 6. Okay. So thinking of the logic here, if we take a look at the green path, this is the path that Bob traveled, right? This is the path, and the green path is what Bob traveled, and that will be a singular path. Whereas if we take a look at the path that Alice traveled, that is in yellow, so that will be a path towards all the leaf nodes. So thinking of what to use, so the green path we will be using DFS because this is from a singular like Bob's node to zeroth node, so we can use DFS to traverse, right? And for uh, Alice, fill the leaf nodes because it is like a branching out and reaching all the various possibilities. So we will be using DFS in that. Okay, let's initialize and find the tree. So tree is a default dict of list for U and V, both nodes in the edges. U dot append and tree V dot append U. Okay, so we have generated the tree, and after we have generated the tree, we will need two things. We will need Bob's path. So Bob path. Let's initialize this to be an empty dictionary now, and let's call a function DFS to find Bob's path. So DFS find Bob's path, and Bob's path will be a hash map, and it will store the node and the steps it takes to reach that node. Okay, so initially the step is 0. We are at the node Bob, right? And we also need the tree. Okay, so we have passed all these things, and because this is a DFS, we will also need a variable to keep track of the nodes that we have already visited, right? So let's send in a set to keep track of the visited nodes. Okay, hash set. Let's implement that function. So DFS self the path current node uh, steps current node tree and visited. So as soon as we go inside as soon as the DFS function is called, let's check the visited. So add the current node to the visited set, and after this is done, let's add the current node to the path. So path current equals steps, and if the current node is 0, we can just return from here, right? Uh, for each node in the adjacent nodes towards adjacent nodes of the current node, let's call a DFS function if it is not visited. If we not in visited and DFS, so we need a condition where which returns true if we have reached the end node, otherwise it returns false if we have not reached the node 0 yet. So let's return true in this case, and for each node v not in visited, we just visit that. So we call the DFS function, and ever if this returns true, we also return true, right? So passing the parameters to the DFS function, so we need to pass the path steps plus 1, the current node will be v, tree, and visited. So we return true if this condition is, if this ever reaches true. If this never reaches true, we know that this is not one of the valid nodes that we can use to reach the 0th node. So we just pop this and remove this from the visited values. So path.pop current node and visited dot remove current node. Okay, and we have to return false. So this fills in Bob's path and the steps it takes to reach Bob's node. And now we know that we have the Bob's path. Let's find the maximum path, maximum income that Alice can have. So maximum income that Alice can have, let's initialize to be a very negative number, very low negative number. And then once this is done, let's write the DFS function. We will be using a double-ended queue to pass and remove, add and remove elements from both sides of the structure. So let's initialize a queue. This is a double-ended queue, and initially let's pass in let's pass in three things. So we are at the current node we are at, the steps we have taken, and the cost, initial cost. Okay, so we will be going till the queue has values. This loop will run till the queue has values, and the first thing that we do inside this loop will be to abstract, to remove out the current node and the steps. Right? The current node, steps, and cost will be queue.pop. So after we have removed this node, now we need to check whether if this current node is a part of the Bob's path. And there are two cases. So if the value of steps, right? So if Bob has not reached this node yet, and if Bob has reached the node yet, Bob has already reached the node, or Bob and Alice both reach the same node at the same time. Okay, so let's write the conditions. So if the current node is in Bob's path and the steps that we have taken is less than what Bob has taken, then we know that Alice is the first person to try to reach that node. So we can add the total cost value to the cost. So cost plus equals amount current. Okay, if current in Bob path and the steps that Alice has taken is exactly equal to the steps Bob has taken, the cost will be amount divided by 2, right? If third condition would be if Bob has already, if Bob is the person to reach the node first, so in that case we will be adding 0, right? Path and steps greater than path current, cost plus equals 0. So this is a condition that we can omit, but let's add it just for the sake. And the other condition is if the node is not in Bob's path. Right? If the node is not in Bob's path, the value of the node, the entry fee at that node will be added to the cost. Okay? So once we have added all the possible values to the cost, if it is the leaf node, then we have to stop the queue there itself, right? So we have reached toward the end, and we can calculate if that income is the maximum income yet or not. And to know if a node is a leaf node, we can see that if a node is a leaf node, it will have only one path going right? So it will have only one path. So the length of the nodes from a leaf node will be 1. So yeah, we can use that. So if the length of tree current is equal to 1, then we know this is a leaf node. Then we can calculate the maximum income. Maximum income will be max of max income and cost. Otherwise, for each node that the node can go to, so for each node v, the current q dot append. Then again, this will be the same structure with 3 elements. The current node v, the steps it takes will be step plus 1, and the cost be cost, right? Uh, uh, there is one condition that we have to also check here. That is, the node is already not the node is not visited. So to keep track of the visited and unvisited nodes, let's initialize a visited hash map. If we not in visited, only then we call this. Only then we add it, and initially when we pop out, we'll just add visited dot add current. Okay. So as soon as we pop from the queue, we just mark it as visited. We find the cost. After finding the cost, if it is the edge node, we just if it is the leaf node, we find the maximum income. Otherwise, we just add the values. And after everything is done, we can return the maximum income. So one condition that we have missed here is to make sure that the current leaf node, the leaf node is not the root node, right? So let's also add that. So if the leaf node, if it is a leaf node and the current node is not equal to the leaf node, so only then we have to calculate the maximum income. And this, let's run the test cases. Looks good. Let's submit. Okay.